conference, I don't think I have to convince anyone here as to the importance of looking for life outside of Earth, be it within the solar system or beyond it. So far, we believe that our best possibility of finding life on another planet is in finding Earth's doppelganger, or Edda Earth, a terrestrial planet around the same size as Earth and residing within its habitable zone, which has been gone over many times today, but in case you weren't listening, is the zone where if there is water on the planet, then it would be in its liquid state. This is because a lot of our theories as to the necessary factors to support life include having access to liquid water. Now, I'm going to apologize before I start. I sometimes have a really hard time saying habitable. I don't know why, but if I butcher it too many times, I'm going to switch over to the liquid water zone instead. But we'll see how I go. All right, so in a paper that we published last year, Dr. Stephen Kane, myself, and all the other wonderful people that you see listed at the top here, we catalogued all the Kepler Hubble Zone exoplanets. We used the data release 24 Q1 through 17 data vetting process, which we combined with the DR25 stellar properties table. From the DR25, we took out the effective temperature of the star and the stellar radius and recalculated the radius of the planet, semi-major axes, and the the flux that was received by the planet to create a more up-to-date data set. We defined 4 different parameters into which each planet fell, and that in turn gave us 4 different tables. The first 2 parameters were to do with the habitable zone. Either the planet fell into the conservative habitable zone or the optimistic habitable zone. So this has already been gone over a fair bit today, but for those who weren't here or were not listening again, so the conservative boundary on the inner edge, which was defined by Koparapu in 2014 at 0.99 AU, is the runaway greenhouse limit, where the liquid oceans would evaporate. On the outer edge, we have at 1.7 AU the maximum greenhouse effect, whereas CO2 greenhouse effect is at its maximum. The optimistic boundary, the inner edge, is at 0.75 AU, which we call the recent Venus limit, which is based on observations that Venus may have had water on its surface around 1 gigayear ago. And the outer edge is at 1.8 AU, we call the early Mars limit, which based on the empirical observations that Mars may have been habitable about 3.8 gigayears ago. So the second 2 are based on planet size, because as we all know, size matters. So the planets could either be within the less than 2 Earth radii bracket, or of all radii. So even though there is a growing consensus that the boundary between the terrestrial planets and the gaseous planets is around 1.6 Earth radii, we chose to use 2 Earth radii to account for any uncertainties that came up in the stellar parameters that we were using, and also the planetary parameters. So we didn't want to eject any potentially terrestrial planets from our tables. So the 4 tables that we ended up with was table 1 at 20, with 20 candidates, table 2, 29 candidates, table 3, 63 candidates, and table 4 with 104 candidates. And each of these tables you'll find can be subsets of the others. So table 1, which had our most stringent parameters, is actually a subset of each of the other tables. So we can see much more clearly with this beautiful graphic, which I've stolen from Sunny Harmon. Thank you, Sunny. the habitable zone boundaries. And we've seen a couple of iterations of this before today, but in case you were asleep, we'll go through it again. How do I go back? There we go. So we have on the y-axis with increasing temperature of the star, and you can see the change of the habitable zone with the increase in temperature. And on the bottom is not distance, but the stellar flux. And you can see Earth lines up with 100%. So planets on the left-hand side of the graph are receiving more flux than the planets on the right-hand side. And so the planets that are depicted here are actually depictions of the planets from our table 2, which is the less than 2 Earth radii in the optimistic habitable zone. So we plotted a histogram of the data set. In the green, we have our habitable zone candidates from Kepler, and the gray is the entire Kepler catalog. And we found that the distributions looked pretty much the same, which was awesome. And so we plotted a power law on each data set, as you can see here. We excluded the first 2 bins from our power laws due to lack of completeness for planets less than 1.5 Earth radii. So the power laws are not meant to represent completeness, but just be a direct comparison of the entire Kepler catalog versus the ones found in the habitable zone. So we saw that there was a very slight difference in the slope of each of the 2 data sets, which implied that we were less likely to find the smaller planets in the habitable zone. But you need to remember also that planets in the habitable zone tend to be further away from their star, and so we are less likely to be able to see them because their orbital period can mean that they don't transit the star often enough to be seen or confirmed, and sometimes their orbital period can actually correspond with the orbital period of Kepler's spacecraft itself, which increases the noise significantly. So after doing the maximum likelihood estimator, we found that there was no statistically significant difference between the 2 data sets, which is excellent news because it means that we can use the distributions of any wide sample of planets and relate it to the distribution of the habitable zone planets. And considering the habitable zone planets are harder to find, this will be really helpful in the future statistical distributions of habitable zone planets. So our next steps, the tables that we created have both confirmed and unconfirmed planets. So validation of the unconfirmed planets is our next priority. Validation of category 1 and 2 candidates is actually underway at the moment, using primarily adaptive optics and Willie Torres's blender technique. With a comparison of catalog with Earth estimates, as Kepler's primary mission was to determine Eta Earth, we can use our catalog with the occurrence rate calculations of the Kepler mission, and improving stellar parameters needs to be continued, obviously. Our Hubble Zone calculation of the boundaries is reliant on stellar parameters. So improving these stellar parameters is only going to be able to help us to refine our gallery or our catalog. And lastly, the category 4 candidates, which this is the most exciting bit for me, was the amount of giant planets that we found in the optimistic habitable zone. So while giant planets themselves are not ideal candidates for finding life, they do open the possibility of large terrestrial exomoons. And so these moons, if they exist, we haven't found any yet, but If they exist, then they would also be in the habitable zone, and so could be great candidates for finding life out in the universe. And at that, I'll leave it there. Thank you for listening.